AB Calculus, Notecard 74, volume of cross sections. This is the 74th video lesson in the series inspired by Stacy McMullen, formerly the Dallas Independent School District, who developed the Notecard system. Now, volume of cross sections, this is a follow-up logically from the last few videos. We looked at the area between curves, right? If you had an area between curves like this, and then by extension you could take this area between curves using the washer method and rotate this area about the x-axis and get a volume formed by rotation. And a cross-section is a further extension where you have some kind of a function. I'm just going to draw it. Let's say we have a sort of a square root function here, and you have an area here, say, and to volume of a cross section is, say that we have the base of this function serve as the base of a square. So you have a square coming up here, and then you create a three-dimensional solid from this. So that's basically what we're looking at. And you're looking at the basic formulas for area. There's a square, which is going to be area equals side squared. You have a circle, area equals pi r squared. You have semicircle, which is area equals pi r squared over 2. In rectangle, area equals length times width. And then you have these isosceles right triangle, base, equilateral triangle, and so forth. We're going to go over a couple problems here. Let R be the region in the first quadrant under y equals 1 over square root of x for x between 4 and 9. Find the volume of the solid whose base is the region R, whose cross sections cut by planes perpendicular, that's a perpendicular symbol, to the x-axis are squares. So what you have is a function here, a graph, that looks kind of like the reciprocal function, except you have 1 over the square root. So the thing's going to look something like this. And you're going to be going between 4 and 9. So you're looking at this area here in between 4 and 9 and rising up. And so this area here is the base of the solid. And then perpendicular to the base of the solid, you have a let's try to draw this a little bit. You have a I don't know if that look. This is a square that emanates here because you're coming up here like this, and the this solid kind of tapers down like this. So you're going to have a solid with a square at one end where x equals 4, and also a square at the other end, and then a sharp edge tapered solid. The square kind of looks like that. So what you're going to do is you're going to take this base, and we're going to integrate from 4 to 9, and we're going to take this function here, 1 over square root of x, and the area of a square is going to be s squared. So if this is the side of 1 squared, 1 over square root of x, what we're going to have is, that's going to be the volume. And so we have that. So we're squaring each side. We're using this s squared formula here. And let's go ahead and what we have here is from 4 to 9. We have 1 over square root of x. And when we square that, it becomes 1 over x dx. Well, the integral of 1 over x dx is the natural logarithm of the absolute value of x. And we're going to evaluate between 4 to 9. And working to the right, we get natural logarithm of absolute value of 9, which is just 9, minus the natural logarithm of the absolute value of 4, which is 4. And simplifying using properties of logarithms, we can reduce these terms of logarithm to a single logarithm. We have natural logarithm of 9 over 4. And that is going to be our answer. So going back to fundamental theorem of calculus would be like we had our big F of B minus our big F of A. And that's all there is to it. Now we have the volume of this shape. Next, find the volume of the solid whose base is enclosed by x squared plus y squared equals 1. And it really helps if you know what this is from your pre-calculus or algebra 2 days, that this is the equation of a circle with a radius of 1. But let's just solve this out without understanding. If we're going to go ahead and solve this equation for y, we're going to get y squared is equal to 1 minus x squared. And if we solve for y, we get y equals plus or minus the square root of quantity 1 minus x squared. And what that looks like is something I'm going to sketch right over here. We have negative 1, 1, y-axis 1, and 1, negative 1. And what you have is this kind of shape here, a circle, a semicircle. It's going to be, that's going to be plus square root of quantity 1 minus x squared. And the bottom half of this circle is going to be negative. And so we are integrating from left to right, from negative 1 to 1, and the base, whose cross-section is perpendicular to the base, are semicircles. So it's like these are semicircles on top. So it's rounded, and that's what the thing looks like. Maybe not a very... So you have a three-dimensional shape that's going to be like a hemisphere that's going to be flat on bottom. And now to integrate that, the area of a circle is going to be pi r squared. And we're going to integrate that essentially. So let's work that out. Our volume is going to be the integral from negative 1 to 1. And we have pi. And the value of our r is going to be this square root of 1 minus x squared and we're going to square that, and then dx. And since we're talking about a semicircle, we're not talking about a sphere on the bottom. We're going to divide this pi in front by 2. And so working below, we have volume is equal to pi over 2, and we have the integral from -1 to 1, -1 minus x squared squared, that's going to square root and square root and cancel each other, so we get 1 minus x squared dx. In the case of cross-sectional, volumes of cross-sectional, you're going to have square roots cancel each other out sometimes. And so working to the right, we're going to have pi over 2, and we're going to have the integral of 1 dx is going to be x, pi over 2x, and we have minus pi over 2 x cubed over 3. And we're going to be going between -1 and 1. And I'm just going to work below here. So we have pi over 2 x, and we're going to have minus pi x cubed over 6. And we're evaluating between -1 and 1. And work to the right, we have pi over 2 times 1, which is going to be pi over 2. And we're going to have minus, we plug in 1, we're going to get pi over 6. We're going to subtract out this amount here. We're going to have -1 times pi over 2. So that's going to be negative pi over 2. And then we're going to have, we'll place in -1, we're going to get negative okay, we're going to subtract out that subtraction sign, right? And we're going to have negative pi over 6. Okay, so really, it's a matter at this point of simplifying. I'm going to continue to the right. So we have pi over 2 minus pi over 6, and we can make that 6. That's going to be 3 pi over 6 minus pi over 6, and then we're going to have minus negative, so that's going to be plus 3 pi over 6, and then we have minus minus minus, so we're going to have minus pi over 6. And working below, we have 3 pi over 6 minus pi over 6, that's 2 pi over 6, plus 3 pi over 6, that's going to be 5 pi over 6. What we're going to get is 4 pi over 6, which reduced is going to be 2 pi over 3. And that's going to be our volume of our cross section here. Now it so happens that if we understand that our volume of a sphere is equal to 4/3 pi r cubed, we can get this volume without using calculus, really, by taking 4/3 pi, and r in this case is 1, and we're dividing by 2 because we only have a hemisphere, so we're going to get 4 pi over 6, which is the same as 3 pi over 2, or 2 pi over 3. So occasionally you'll have these calculus problems that can be actually worked out without calculus. So I'll just put down r is equal to 1. So that's it. I hope this has been helpful to you. Good luck, and thanks for viewing.